All right, let's get started. Can you hear me well? Can you guys hear me?
Yes, sir.
Yes.
All right, good. So the course is astronomy and cosmology. So here we are going to look at the solar system and beyond. We are going to look at the galaxies, the universe in very large scale, and we gonna look at some philosophical questions, right? So this is basically physics, right? Not engineering, but we don't want to bog down into physics. As you know, physics is much more complicated than engineering, okay? And there's a lot of philosophical questions that you need to think in a different mindset, okay? Not engineering. And also I want to emphasize you there's a lot more than engineering, right? The whole purpose of this semester is to make you more versatile, right? Versatile, complete human being rather than just a professional engineer, okay? So it's a big thing, okay? So you have to be very serious about it, because now you are going to get into say professional um, role as engineers in this country, and then over the years we will be mature people, right? And who take decisions, right? So so you can't do all these things with only engineering, right? There are a lot of other things you need to uh, learn and practice, right? So to help you to become a mature person, a visionary person, uh, is the objective and intention of this kind of courses. Not only astronomy and cosmology, but other things as well in this semester. But particularly astronomy and cosmology is very fascinating subject, and just by engaging uh, alone, you get a lot of development in your vision, right? In your vision around everything, right? Okay, so let's get started with the solar system. The first thing I want to talk to you about is actually the solar system. I'm sure this is something you have heard before, right? As a kid, right? But now we're going to look at it in a much more serious manner, right? So the objectives of the this particular topic, solar system, right? By the way, there's something else I want to talk to you upfront is that you need to have objectives in everything that you do, right? Objectives. So when you say objectives, the different hierarchical levels, right? If you look at the objectives of your life, right, that is at the top. That is at the top, right? That is a very big thing, and maybe just one or two objectives, not too many. But when you bring it down to, let's say, your objective as a university student, right, then that's a different, um, relatively, I would say, small, doesn't mean less important, right? But a small objective or objectives, right? Then when it comes to your field of expertise, you have other objectives. When you sit for the semester exams, you have that objective, okay? Like that, you set your objectives based on the context, based on different roles that you have to play, based on different responsibilities you undertake, okay? So this is a dynamic lookup table kind of thing, all right? You have in your brain your life objectives, what you want to be at the end of the day, but you don't bring it every moment, right? That is there back in your mind. That is the guiding question or guidance that you get continuously. but you don't take it very apparently, very obviously for everything that you do, but it has its influence. Okay, so again, if it comes to the, let's say, syllabus, when we teach different subjects, let's say astronomy and cosmology, right? There are objectives, as I explained to you, right? These are big chunks, big objectives, right? To become a visionary, more versatile person, human being, right? Who knows about, say, beyond textbooks, knows about the world and beyond. Okay, so but when you take different subjects, say for example solar system, within that context you have different objectives. Okay, so these are the objectives here, particularly uh, with regard to the solar system subject that we are going to embark on right now. So what are they? The first, the first one here is to understand our planet, sun, and the solar system. So that is number one, right? This is a small objective. It's not as big as your life objectives, like I want to be a good human being, right? That kind of thing. Then the second one, to understand the formation and evolution of the solar system. This is extremely important to understand how something has evolved, how it started its journey, the birth, and how it evolved into the present shape, right? And again, what's going to happen to that thing in the future and how it's going to end, right? So this process is extremely important to know about these things. Even in mathematics and other subjects, you hear different people, right, inventing various things, right? So it's important to understand how these things developed over the years, over the last, say, couple of centuries, right? Just learning the theory, the laws of physics, etc., right, it's not that interesting, right? But you can make it very interesting if you look at the history of science, history of mathematics, how it evolved and all. So why don't you listen to some oration, a speech, right, of somebody, let's say Euler. Recently, I heard one of the speeches, orations from a British mathematician, right? Oh no, he's a US mathematician, about Euler. You know Euler? He's one of the greatest, right? All-time great in mathematics, Euler. You have heard of it, right? So if you just listen, it takes about an hour or maybe 90 minutes, right? You will be amazed to see how these brains work, right? Very special type of brains. Those things are very important to polish your thinking, right? Otherwise, you will be very hard engineer. Okay, so then the third bullet, understand the structure of the universe. Very important. So this is basically not only solar system, the DE2410. I don't know how you call it this semester. These codes are going to change, right? Don't worry about it too much, right? This is what I used to use DE, Dean Engineering Course 2410. But when you offer it to other disciplines, undergrad division, change the code. I will check that out. Don't worry too much about it. To understand the structure of the universe. So this is a huge undertaking, right? Nobody has seen the whole universe. So just like that we see out there of the window, you can see your environment, right? You can't see the universe like that because you are inside in the universe, right? But there are ways to figure out how it is using measurements and 3D modeling, etc. Okay. Then the fourth one, to understand life on Earth and search for extraterrestrial life. This is going to be very fascinating area. Is there any extraterrestrial life, any life beyond the Earth? The answer so far is no, firm no, but it's very unusual. Why are we alone in here? If the life fostered here on Earth, why it is not possible elsewhere? Oh, some people say, no, don't worry. There's life out there at this very moment. As I teach you, as you listen to me, some other place in the universe that we don't even uh, see anything about, right? There are countries, cities, universities, and lecturers teaching and students learning. It's quite possible, right? It's not impossible. So these are mind-boggling, right? Questions that freezes you for the moment, right? Now, if you have to believe there is another world somewhere where there are universities and lecturers teaching just like I teach you TE 2410, right? And there are students listening, and they have all sorts of other problems like COVID. They are fighting against the COVID, and how they would look like. Are they like humans or different? So these questions research you, so drive you crazy, right? Sometimes. That's why I said thinking about this kind of thing will make you a complete or more versatile people, right? Whatever profession you are in, whether it is medicine, engineering, whatever, then ultimately to become a wise man, there is a final objective with correct understanding about where we live, about the earth and our place in the universe. So now, because our education system does not allow you to cross over to the other fields and but try to make you more and more into a narrow area, right? You're losing your tolerance. You're using your vision. This is going to be a problem. Now you know there are very highly educated people. I know a lot of people like that, but they can't even go home from, say, Town Hall, Colombo. If you give them some money, get the bus and go home, they can't even do that. But they were highly educated people. So there's something seriously wrong about our education system. It doesn't allow people to become humans, right? But try to make them robots, right? They know one thing and only one thing. So that is why these subjects are very important. As you become professionals in certain area, you always need to have your hobbies and always need to have some time to read books, study about other areas, right? That's very important. So our learning objectives for this particular lecture, solar system, right? The first one are these. What constitutes the solar system? What are the elements of the solar system? And understanding the scale model of the solar system. The scale is also something that everybody really wants to know about, right? Now, if you look at your house, I do know how big it is, small house, big house, like that. And then with respect to your house, the other things around you, scale modeling, right? And also sometimes some people can actually guess, say, if they see a lamp post on the roadside, how high is that? And if they see a big a vehicle, how long is that vehicle? Can you guess it? How many feet, how many meters, like that? So try to quantify things around you and put it into 3D scale, uh, right? That's important. So what about solar system? There's a huge structure. Can you understand how big it is, how big the planets are in relative scale, and their interdistances, right? We're going to look at that and see, test our knowledge about it. And also origin of the solar system, how the solar system, the sun and earth and the other planets came to be, and also fate of the solar system. What's going to happen to the solar system in the future, right? So these are the objectives of this lecture, solar system. I think most of you have seen this photo, right? This photo is not correct, I would say. And this is correct only to the scale or size of the planets. right? You can see maybe over here, Mercury, the first planet, Mercury, uh, then Venus, somewhere here, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, maybe over here, Pluto, right? This is not the way they are there, but this is uh, how big and small they are, right? Biggest planet is Jupiter, then Saturn, Uranus, Neptune, and then come over here, right? You can see very, very small planets over here. You might wonder why are they very small? Have you ever thought of that? And why after this point, all of a sudden, planets are big? Okay, so there should be some reason, right? Physical reason as to why these planets are very small. And these ones are very, very big, very clear separation. This cannot be arbitrary. Okay, there should be some science behind it. Have you ever thought of that? Have you ever been curious about it? Hmm? I'm sure you have seen this, right? Have you ever thought of as to why the first four planets are very, very small compared with the other ones? So these are things we are going to look at it, right? Because they just stem out of curiosity, right? And also one thing I want to tell you here is that this scale is hugely incorrect. The scale, don't don't believe that the distances between the planets are like this. This photograph does not represent the distances between the planets, but it is accurate in terms of size, the diameter of these planets, okay? Not the distance. Then here, this is somewhat old, but I don't want to give you, say, latest up-to-date information. That's not the purpose. The purpose is to be more physically informed about the solar system. So therefore, this photograph is good enough. So this is an assembly of photos, right? What are they? So if you look at Earth, it's like this, right? Um, you can see selected moons of the solar system, right? With Earth for scale. So if you see the Earth here, Earth is not a big planet. If you see this one, Earth is relatively very small, right, compared with the big giants. And there are very small other bodies in the solar system. We call them moons, right? You can see our moon, right? Earth and moon. So then if you look at Mars, Mars has two moons, Phobos and Deimos. These are going around planet Mars. Then you have asteroid belt, a lot of small bodies, right, between Mars and Jupiter. They have got some of them have got names even, like Ida or Dactyl, and there are other few names. Asteroids, they were too small to be named. And then comes Jupiter. Jupiter is so big. Here you can see the moons of Jupiter, not Jupiter, but moons of Jupiter. And they are as big as our moon, and also somewhat closer, comparable to the size of the Earth even, right? So they are Jupiter, Io, Europa, Ganymede, and Callisto, right? The Jupiter is so big, and their moons are also big. And then we have Saturn. Saturn is also a giant planet, big planet, next to Jupiter. Saturn has so many moons going around it, like Mimas, Enceladus, Tethys, and Titan is very famous, right? The satellite of Saturn, Titan. Then have Uranus. Uranus have a lot of satellites around it, natural satellites or moons. Neptune has Just few among them. Triton is very famous because it's so big. Okay, and then Pluto has only one moon, Charon. Pluto and Charon are very like comparable in size. That is another interesting phenomena. Usually, we recognize the mother planet and the moon by their size. Usually, the mother is relatively big, right? Relatively much bigger than the moon. Here, if you look at Earth and Moon, this is also not very prominent mother and moon body. If you see Earth and the moon is not very small compared with the Earth, right? They're comparable. So therefore, sometimes you can call it double planet system, double planet, right? And the case for Pluto is even more significant because Pluto and Charon, you can't see Pluto here as a photo, but Pluto and Charon, they are like almost equal to each other, right? So therefore, we better call it a double planetary system. And then after that, you have some other small bodies like Eris. We don't recognize them as part of the solar system, just outside the solar system, right? And the space continues, and there's no limit for that. There are small bodies beyond Pluto. Okay. Now you have seen the members of the solar system, the planets, the moons, asteroid belt, etc. Right? The members of the solar system are these: Sun at the center of the solar system. Right? It is the biggest of the solar system. There's nobody comparable to the Sun in size and energy, etc. Okay, it holds everything together. Then we have 8 planets. They are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. And we actually don't call Pluto a planet. Okay, so International Astronomical Union many years ago, decades ago, decided, right, eventually after a long discussion and debates, etc., that Pluto is not qualified as a member of the planetary system, right? It's a captured body. There's evidence to prove that Pluto was not there initially when the planets were born, but later at some point, Pluto was traveling. It came to this area and then captured by the sun. And after that, it was going around the sun in an orbit, and it looks like the 9th planet, but it is not a planet. It is a captured body. Okay. And also more than 180 natural satellites, all the satellites you have seen here, right? Only some of them. Altogether, there are more than 180 natural satellites. And there's a large number of small bodies, very small bodies, comets, asteroids. Sometimes you can see comets, right? Getting closer to the sun, and then you have the tail, if you have a small binocular or a telescope, right? When there's a comet up in the sky just after the sunset, when the sun is there, you can't see anything, but if you let the sun set before it is too late, maybe within an hour or two after sunset, if you look at the west direction, you can see the comets. If there is a comet, okay, you can't see it every day. I'm getting some noise from someone's phone. Could you please mute your phones? If you want to speak to me, just unmute and talk to me. Um, I don't know whether you are lucky to see a comet in your lifetime. I have seen one or two, but that was a long time ago. And I have seen a comet falling onto planet Jupiter in 1990s. The comet, as it reached the planet Jupiter, the one single body was fragmented into about some 16, 18 pieces, and then they fell onto the Jupiter one after the other, right? So I was fortunate to see some of these very rare events. I don't know whether you will ever have this opportunity to see, but if you ever have that opportunity, don't miss it. It's a once in a lifetime opportunity to see, right? And also time you can see the eclipses. Recently there was a solar eclipse. We experienced it here in Sri Lanka. Every couple of years you will see solar eclipses, but it's very short lasting thing. um, if the sun happens to be within this area, we can experience it. Otherwise, it's unfortunate. But there are a lot of lunar eclipses are common and last a bit longer than solar eclipses, so that you can see it generally better chance, right? Don't miss these things, the heavenly phenomena. Uh, the comets are very important for other reasons also, because there's a theory that Earth didn't have water at the formation. When the Earth was formed, a lot of people say we are too close to the sun. We are too close to the sun. From the sun to the Earth, it's like 150 million kilometers. 150 million kilometers. Even now, you can see it's very hot, right? Even now. But back in the day when Earth was forming, it was so hot, and there was no chance for water to present here. They would have all evaporated. That's what the science says. So if it is the case, how did we get water here? And some says there were a lot of icy bodies around, right? Not very close to the sun, but farther away, there is ice. Comets, they have water, frozen water. They have other frozen gases, and that's how comets get the tail. And as the comets, some comets, as they reach right towards the sun, there's a chance that some of these comets uh, uh, head into the earth and probably would fall on the earth, bringing water. So we are talking about long, very long time scales, and that's how earth got water, accumulated little by little by little. Okay, so there's theory behind that. Comets are somewhat bigger objects, like 10, 15, 20, or even be 100 kilometers in size. But asteroids are very, very small bodies, like not more than a kilometer or two. But most of the asteroids are very small. And also, if you just stare at the sky when it is a new moon, very dark, if you are patient enough, if you can stare to the dark sky with all the lights off around you, you might be able to see shooting stars, some straight line light, right, passing, right, uh, say you can see it some places, right? It's arbitrary, it can happen, come anywhere, right? So if you give it, let's say, some 10, 15, 20 minutes of time, you can see some of these falling stars or shooting stars. These are actually very, very small asteroids. Can't say even asteroids, right? Very small particles, grain particles, so maybe a gram or two, right? It's just dust. But their bigger brothers are asteroids, right? Usually they are there between Mars and Jupiter. Mars and Jupiter. Okay. Then the medium, interplanetary medium. So between planets is not vacuum. It's not perfect vacuum. It's very low density medium, but still not vacuum, right? Um, and then we have Kuiper belt and Oort cloud. Kuiper belt is beyond Pluto, right? We believe that there is a belt kind of thing, like asteroid belt between Mars and Jupiter. There's another belt, Kuiper belt. And then in the far distances, there's a sphere kind of thing, very, very big. We call it Oort cloud. And we believe that some of these comets are actually coming from either Kuiper belt or Oort cloud. It's a very rare event, right? That's what some scientists believe how we get comets, right? Now let's look at the location, our location in the Milky Way, right? So when we find out our location, you know that we always use a reference, okay? When we locate our position, let's say 0 latitude, longitude, right? Spherical coordinate system, lat long. So that's how we locate ourselves, right? So if you look at the solar system, the reference is the Milky Way galaxy. So we are in a big structure like this, big structure like this. So this entire structure is made of stars. You can't see the stars here, right? They're all over, like in spiral arms, like a lot of stars, right? And in the center, you have stars more closer together, and then spiraling out like 4 arms: Cygnus, Perseus, Sagittarius, and Centaurus, right? And it rotates like this very slowly. And our sun and the solar system is somewhere over here on the Orion arm. Orion arm is a somewhat shorter arm compared with the other arms. Okay. We will talk about galaxies maybe later. For the moment, you think about that one of the building blocks of the universe is the galaxy. There are different types of galaxies. This is spiral. There are other shapes, elliptical, etc. And this is most beautiful and regular structure of stars. Okay. So if you look at the distance from the center of the galaxy, we have given it a name like Milky Way, right? Because when you see from the Earth here towards this direction, right? Some days at night, if you look at the towards the south, okay, if there's no moon, it's dark, then you can see the center of the Milky Way, this area, right? Like a white cloud. You might sometimes misunderstand it as a isolated cloud, but if you look at that direction when there's absolutely no clouds, it's not a rainy day, it's a very clear sky, you can still see a small patch, and that is the center of the Milky Way. right? So as one of the exercises, I asked you to search the web, right, and figure out yourself where to look for the center of our own galaxy, Milky Way. Okay, during which time of the year and which direction that you can see the Milky Way. Okay, so all of you, I think you need to do this yourself, right? It doesn't, you don't have to um, keep yourself awake overnight, right? Do Google it, figure it out where to look, and maybe during the course at some point, I will ask one of our visiting lecturers to come and teach to you about Stellarium. Stellarium is the software of the Sky Simulator. You can download and run it. It's free, open source. And then if you give your location, Sri Lanka, latitude, longitude, you can find that on Google and give as input to Stellarium, and then simulate your sky. Give it the date and time. Let's say today, 3rd of May 2022, 7:30 p.m. Okay, you go out. What is the sky you see? You can see it on your screen. Then you use your mouse and move it here and there, different directions, north, south, east, west, right above you, right? It will show you what are the stars you can see. It's highly educational. And there's another version of that, mobile version, right? You can use that one also, and it's more convenient. You can bring it outdoor. You can bring it outdoor, and you can haul it against you, right, to whatever direction. And using the app's sensors, the compass and tilt sensors, the app figures out where you are looking at, your direction. You don't have to give south, east, whatever. When you hold it towards the sky with your screen towards you, it will show you what is behind you, what is on the sky, right? In that direction. So I really encourage that you download this software onto your mobile, onto your laptops, and try it out. It's very easy. Nobody has to teach you. But during the course, I will get Shakya to teach you. Shakya is one of your seniors, graduated from electronics about some six years ago, right? He will teach you about stellarium. Right. So that is the first exercise. There's no assessment. You don't have to report anything to me, right? Just let me know what you see. But sometimes I might make an assignment for you on this one, right? If I do that, I will give the instructions as a paper, right? And upload it to Moodle so that you can download and fill it and submit back to Moodle, right? Right. So that's where we are, okay, in the Milky Way. So the distance from the center to the sun, right, is about 30,000 light years. 30,000 light years. The light year is a unit of distance, right? One light year is, as you can see it over here, 9.460528 in 10 to the 12 kilometers. That is trillion kilometers. Say 9.5 trillion kilometers. So that is the distance light travels in 1 year. So you know the speed of light, right? 300,000 kilometers a second. You multiply it by 60 to make it a minute, 60 make it to hour, 24 make it a day, times 365.25 to make it 1 year. And you get this number, okay? So we use light years to measure very, very long distances. In astronomy, we talk about very, very large scales, right? Very, very large, long distances. So we can't talk about in kilometers, meters, whatever. We need to have big scales in astronomy. That's why when we say it's an astronomical problem, when you talk in normal English language, we say when it's a very, very big problem, we say it's an astronomical problem, right? When it comes to astronomy, cosmology, everything is very, very big. Okay. Right. So, and sun is not static, as you know, this is spiraling, rotating like this, right? So the linear speed of the sun, because this rotation, every object, every particle gets a linear speed, uh, depending on where they are, right? And also the angular speed of the whole structure. So it has been estimated that the Earth's and the solar system whole thing together is moving at 220 kilometers a second. See, huge speed, right? 220 kilometers a second at this point, right? So the structure is so huge that even with this very high speed, it takes about 220 to 250 million years to complete one route. So go around the central bulge and come back to the same position. It takes about 220 to 250 million years. Okay, so these numbers are crazy, right? And since the formation of the structure, right, the solar system has completed at least 18 such revolutions. We have only gone through 18 such revolutions. Okay, so this is the basic structure as to where we are in the universe. So universe is much bigger than that, but for our discussion, this is our reference. All right. So there are other questions. Then you might ask me, okay, where is the Milky Way in the first place? There are some answers for that. Um, without keeping you on hold for too long, I would say there are about another some 30 odd galaxies around us. This is just one of them. There are other galaxies close by, relatively close by, relatively, okay, like a cluster. We call it local cluster. Local cluster. Milky Way and nearby some about, I think it's about some 30 galaxies. I will tell you the exact numbers maybe later, right? That is a small group of galaxies, relatively closer together. That's why we call it local cluster. So the local cluster is the reference for the Milky Way, our galaxy. And the Milky Way is the reference for the solar system. And the solar system is the reference for the Earth. And Earth is the reference for all the countries in it. Okay, so it goes like that. So if you go backward from the countries to the Earth, Earth to the solar system to the galaxy, galaxy to the local cluster, then you are in trouble. Where you draw the line, okay, this is the point I can perceive. Beyond that, there's no point. Okay, so that's what it is. If you haven't thought of that direction so far, maybe now it's time to just think about it. But I'm sure you will end up having more questions than the answers. Okay, but it's okay. We don't need to have answers for all the problems, right? But we need to know these are the problems. Just forgetting things is not good. Then you think that there's nothing there. No, there are problems. Even though you don't solve them, you are unable to solve it. It's okay to know about it. Okay. Right. So we continue our discussion, try to consolidate a bit more on the location of the solar system in the galaxy. Now this time, this is another artistic illustration of the galaxy, edge on. The previous one is from the top, like plan view, aerial view, and now it is from an edge, the plane of the galaxy. So galaxy has a plane, of course, right? There's nothing much above and below. Everything is like on a plane. So this physically consistent, because as you know, when things are rotating like that, so then it becomes flat surface. Any any uh, any multi-body system, I think if I talk like that, you might understand better. Um, uh, a collection of particles, collection of objects, they stay together because they are intergravity, right? They don't just scatter and move around. Because of gravity, they stay together, that you know. But if one or two of these objects, they have very high kinetic energy, they will escape the gravity, right? So let them escape, and we don't know where that energy comes from, right? So therefore, it's reasonable to assume that a collection of bodies stay together. Okay. So, and if they rotate, then what happens is that because of gravity, the particles come closer together. The volume contracts, right? Volume reduces. So then it starts spinning faster. You know that because the conservation of momentum. And also the object, uh, the collection of these particles, maybe if you assume initially they are randomly distributed like in a three-dimensional structure, and when they start spinning around a certain axis, this three-dimensional structure is going to be reshaped into a flat disk, okay, normal to that axis of rotation. So these are all physics and you guys can understand it. So if you look at the galaxy now, even though it may have started with some random shape, irregular shape, now that it has gone through some of these revolutions, it has become like a flat disk. Okay, flat disk. But if you ask me, can it get to this particular shape just in 18 or 20 rounds? I have no answer. Sorry, I don't know. Right? This is what it is right now. So from the edge on, you can see the disk, the sun is over here, and the distance from the center to the Earth is some 8 kiloparsecs. Kiloparsecs. Earlier, you saw it like how much? 30,000 light years, and this distance, right, is in a different distance unit. Like parsec is about 8 kiloparsec. 8 kiloparsecs, right? 8,000 parsecs. It is like 30,000 light years. 30,000 light years. So one parsec is 3.262 light years. So the parsec is a new unit, right? It's longer than a light year. So in astronomy, you can uh, uh, you can measure distances using light years. The definition is the distance light travels in 1 year, or in parsecs. What is the definition? So for that, I want you to pay attention to your left-hand side of the illustration. So what is this? Well, you can see the sun over here, right over here in the middle, and this is the orbit of the Earth. We are going around sun, okay? The sun is going like almost a circular orbit, but it's actually an ellipse, right? Eccentricity, it will tell you it's closer to a circle. And you can see the semi-major axis and semi-minor axis here. This is a stretched, elongated version. Actual Earth's orbit is not that elongated, right? The distance from the sun to the Earth, right, is about 150 million kilometers. 150 million kilometers. It varies because it's not a circle. If it's a circle, it doesn't change, but in one direction, it's closer to the sun. On the other side, is a bit farther away. In this illustration, you don't see it like that, right? But actually, it's closer to the sun in one direction. So actually, it goes from 147 to 152 million kilometers. But let's forget about this variation, but let's call it 150 million is the distance. Average distance from the Earth to the Sun is 150 million. Okay, all right. So then you can see if you go out at night and you can see the stars. So these are the stars, like a screen, right? Like a screen, you can see all the stars very, very far away from us, distant stars. We are not going to measure distance to these stars because they are far away. It's like the edge. But there are other things relatively closer. These are the kind of objects that we want to measure distance to, right? Like, for example, this particular star. It's not one of those stars on the screen, on the edge. It is a relatively nearby star, and we want to measure the distance to this one, right? Now you have the Earth here. Let's say you have a camera, you want to take a photo of this star at night. And when you take the photo, you can see the star here, and right behind that star, you will see this particular area. And on your photo, you can't separate this star or whatever that object from the other background stars. You will see them on the same photo, but you can see this particular star somewhere over here. Okay, between these two stars maybe. So after that, what you do is you wait for 6 months. After 6 months, you come over here to the other side of the Earth after 6 months, okay? And you stare at the same object and take another photo. So when you do that, now you can see this particular star against these background stars. Okay, 6 months ago it was here, 6 months ago it's here. You have two photographs, and if you in the two photographs you can see these stars 1, 2, 3, 4, 5, 6. You can clearly identify these 6 stars, right? They have not undergone any change, identical positions in both photos. But there is another star, this one, right? In the first photograph it was in between these two stars, and the latter one, after 6 months, that star is over here. Then immediately you understand that this particular star which is moving back and forth, and after another 6 months, maybe after 1 year from the first photograph, if you take another one, you will see the object going back to the same position. So it's moving back and forth with respect to the background stars. So if the star is closer to you, you will see huge variation back and forth. If the star is farther away, you will see small motion back and forth. Okay. So if you measure this angle from here to here, right, the whole thing is 360. But if you measure this angle and divide by 2, you call it parallax angle. Parallax angle. Right? And the parsec is the distance for a nearby star which has 1 arc-second parallax angle. Okay, 1 arc-second parallax angle. So any star which has smaller parallax angle, which means it's farther away, right? If a star has a larger parallax angle than 1 arc-second, is close by, right? So if the parallax angle is exactly 1 arcsecond, the distance to the star, we call the star is located at 1 parsec. 1 parsec. And if you do the calculation, you can see 1 parsec is 3.262 light years. So that's the definition of parsec. Okay. Right. So now I want to give you a little break, 5 minutes, right, and come back for a small quiz. Right. Just maybe, yeah, maybe 8 minutes, 8 minutes, right? And after that, we'll do this quiz. All right. So I'm going to give you a little questionnaire. Why don't you take a little piece of paper? All right. This is just a little exercise. So I need you to engage actively. So this is the first question I'm going to ask you. You have some whatever knowledge about the solar system. You have read about the planets, the sun, etc., right? But I know you don't have sharp memory about the distances, etc. So therefore, this is not a serious assessment. Actually, it's not. I'm not going to take this as any form of assessment. This is for self-evaluation. Okay. So the first question is, to begin with, this part is not a question, but it's information for you. Useful information in the following questions, right? The size of the sun, let's say it's 1.5 meters. 1.5 is a measurable distance. You know, everybody knows to measure 1.5 meters, right? If the sun, the diameter of the sun is 1.5 meters, right? Then you try to figure out this answer. What is the size of the earth? What is the size of the earth? You write it down, the first question. Size of the earth. Get a piece of paper. The first question, what is the size of the earth? To the scale of sun being 1.5 meters. To the scale of the sun being 1.5 meters. If the sun is 1.5 meters, what is the size of the earth? First question, think about it. Write your best answer. Okay. Second question. How far is the sun from the earth? How far is the sun from the earth? Do not do Google here, right? You just write what you think. As I said, this is not an exam. This is a self-evaluation. You measure yourself. You judge whether your guess is correct, how correct your guess is, right? How far is the sun from the earth? And some people I know, when I ask these questions, they go to the Google and find out the distance and divide by the ratio the other way around and then calculate. So I don't want you to do that. Anybody can do that, no? These are very simple questions in that respect. So that's not what we are going to do here. You try your guess. You try your guess, okay? Third question, how far is the moon from the earth? Earth and moon. How far is the moon from the earth? And remember the scale is sun being 1.5 meters. Okay, this is the scale. Next question. How big is the Jupiter? How big is the Jupiter? The Sun is 1.5 meters. How big is the Jupiter? Next question. How far is Jupiter from the Sun? How far is Jupiter from the Sun? So this is going to be a very interesting quiz. It's a nice game kind of thing, okay, for you to judge your perception of the solar system, right? Try to quantify the distance and the size. Next question. How far is the Saturn from the Sun? Saturn, this time Saturn. Okay. Next question. How far are the Uranus and Neptune from the Sun? Don't worry too much about Uranus and Neptune. Take them together, right? It's anyway a long distance, right? Roughly, how far is it? Uranus and Neptune together from the Sun. And the size of the Sun is 1.5 meters. Next question. How far is the nearest star from the Sun? Now we're going to go beyond our solar system to the nearest star, right? You know, the galaxy, right? It has about some 400 billion stars. Some 400 billion stars, right? These are crazy numbers, but this is what scientists believe. Then the nearest one, by the name, some of you guys know it, Proxima Centauri. Proxima means proxim. Proxima means closest, right? Proxima Centauri. So how far away Proxima Centauri is from the Sun if the Sun is 1.5 meters in diameter? Okay. Proxima Centauri. 4 billion stars in our Milky Way. This is the closest one. And how close is that? Now go through the entire set of questions. If you miss any one of those, you can rethink about it and write it down. Write some answer. If you want to correct, cut it and write the new value, new answer. In a moment, I'm going to show you the correct answers. And you can compare your answer with the correct answer and see how close you are or how far you are from the reality. Okay. This is in a way the understanding of the physical world around you, right? And also, I would say this, if you are uh, plus or minus 50% close to the correct answer, you can say you are correct. Your answer is correct. Let's say your answer is 10. The correct answer is 10 for any of these things, right? The correct answer is 10. So if you have written anything from 5 to 15, we can consider as correct. So I'm giving you 50% tolerance, plus or minus 50%. And if you get anywhere closer, right, between minus to plus 50%, your answer is correct. So with that marking scheme, let's see the correct answers, right? I want you to count how many questions that you have answered correctly. So we have 1, 2, 3, 4, 5, 6, 7, 8 questions. The first question, the answer is 1.4 centimeters. 1.4 centimeters, like a big grape. Like a big grape. That's a good start, right? If the sun is 1.5 meters in diameter, think about it. It's like average height of a person, average height of a person, right? 1.5 meters. It's a bit too high, right? And then the earth is like a grape. It's like, in a way, it's like you stand up with a grape in your right hand, between your thumb and the first finger, just a grape. You are the sun, the grape in your fingers is the earth, right? So imagine that as the reality. This is the comparison between the sun and the earth. You can imagine how small the earth is compared to the sun, okay? And by the way, now when you mark your answers, get plus or minus 50%. This is like 0.7 to 2.1, right? 0.7 centimeters to 2.1 centimeters is the range. If your answer is within that range, you're right. Good guess. Good guess. Right, now, can I see how many of you have got the answers correct? Can you raise your hands, please? Those who have got the correct answer. Answer between 0.7 centimeter to 2.1 centimeter. We have one already. Theologian Senanayaka. Congratulations. I think your guess is right. This is not an easy question, right? I think only two. I'm not surprised. I'm not surprised. Some years I get 0. This is not common. Nothing wrong with you. Right? Let's go to the next one. How far is the sun from the earth? This time it's the distance. How far away we are from the sun? 160 meters. 160 meters. Now, think about the same analogy. So you as the sun, you are standing, and earlier you had the grape in your fingers. Now this time you bring the grape 160 meters away from you, and now you can't even see it, okay? It's a grape at 160 meters. Can you see it? No way. You can't see it. That is the distance between you and the grape. Okay, that is why we are kind of safe from the sun. From the glowing sun, we are safe because we are not that close, 160 meters. So if your answer is in between 80 to 240, you are right. 80 meters to 240 meters. You are right. Can I see how many of you have got the answers right for the second question? Raise your hands, please. One answer. Who is that? I can't see your name, but I can see the number. Who has got the answer right? Oh, no, no one. I got a hand raised maybe from the previous question. Okay, all right. So nobody has got it right. So again, I'm not surprised. I'm not disappointed, right? You also don't get disappointed, right? It looks like a simple question. You have solved much more complicated problems. But you understand now something different, right? Something very valid in your life. Such a simple thing we can't solve because it doesn't matter how simple, how complicated the problem is. It all depends on whether you have studied it seriously, whether you are an expert on that. Okay, that's one thing, one lesson. The second lesson, we should know what we know and we should know what we don't know. And you can see a lot of people around you, you can see, right? Some doctors, they talk about engineering and geology. They have not studied that inside out. They can talk about general things, but when it comes to a tough question, they better be quiet or do their homework and come back. And we have seen some engineers talking about medicine and agriculture. There's something you can talk about in very general format, but when it is a bit serious, you better be quiet. Everything is like that. Okay. Everything is like that. So it doesn't matter how simple or complicated the thing is. If we have not learned about it, everything has a science and art. Okay. Even like cutting bread, right? And sweeping the floor, changing a bulb, light bulb, taking water from the well, right? There is a science and there is an art. There's a proper way of doing things, right? Everything has some science and art. So if you don't know that, even though how simple that is, the thing is, we will fail if we try to engage. Okay, that is one thing we need to remember in this exercise, right? We need to learn that the whole purpose of education is not to get humiliated, not to get upset, or not to get disappointed, right? Not to get yeah. So the purpose, the objective is to understand the reality, to understand the reality. Okay, and then what you know, what you don't know, and then with that you can increase your domain by learning peripheral things around you. When you want to live as a human being, as I said initially, you can't live just because of you are an engineer, right? You have to attend to day-to-day things in your family, your neighbors, and then you have to respect them, different professionals, right? And if there's a issue in about water, about food, about other things, there are other experts. You have to be humble enough to get their opinion on you, right? So like that. So we can simply fail, we can miserably fail with a very simple problem which is out of context, which is out of our own field. If we want to engage and change it, we can simply fail. So that is why it's very important that we respect different professionals and get their second opinions, their views in different problems, right? Let's move on. Um, How far is the moon from the earth? Moon and earth, this is relatively close by, so it's about 40 centimeters. Earth is like grape, moon is even smaller, and they are 40 centimeters apart. 40 centimeter, everybody understand 40, what 40 is relatively close by. And if you have got this between 20 and 60, your answer is correct. Can I see how many of you have got the answer right? Please raise your hands. The distance between Earth and the Moon is 40 centimeters. Anything from 20 to 60 is correct, right? But we don't have a correct answer for that one. That's the reality. Time to time you can see the answers, but I'm sure you are doing it honestly, so I don't worry too much about it. Answer to the next question. How big is the Jupiter? 15 centimeters. Jupiter is like 15 centimeters. I think it's like a football. Okay, it's like a football. Slightly smaller than a football, I would say. There's an answer. Delogian. I think Delogian got the first one right, and I got 70 centimeters. Why don't you take it as correct? Right? Yeah, I'm okay. So 70 centimeter. Correct one is 40, but Delogian has got 70. Yeah, you are right. You scored 2. Yeah, good. How big is Jupiter? 15, like a football, slightly less than smaller than a football, right? Compare it with the Earth. Earth is like uh, a grape, 1.4 centimeters, like a grape, and the Jupiter is like 10 times of that, 10 times bigger. Okay. And then how far is, by the way, any answers, any correct answers to that one? Jupiter. Answer is 15, but anything between 7 to about 21, right, is correct. So any correct answers for that? There's one. There's one. I hope this is for this particular question, not the previous one. The hand going up. Yes. Again, this is from Delogian. Yes. Very good. And then next one. How far is Jupiter from the sun? My God. It's 750 meters. 750 meters. So it's like how much? If you look at it from the university along that main road, I think 750 meters is somewhere down the road, near to, not as far as the junction, Katwa the junction, maybe at the foot of the mountain, right? That paddy fields or the marshy lands, somewhere there. 750 meters. Right, from the sun. So you keep counting your scores. Finally, we will get to the accumulated value. The next question is, how far is the Saturn from the sun? 1.5 kilometers. 1.5 kilometers. So that's probably beyond the junction, the junction from the university, right? And the sun is like 1.5 meters, like your height, average height. And about 160 meters away, you have the grape, that is the Earth. And 750 meters away, you have the Jupiter, like a football. Now see, you can imagine the scale distance model gradually. The sun, the moon, the Jupiter, and then the Saturn, right? The whole purpose of this quiz is not to not to disappoint you with your answers, but there's a big satisfaction as you see it, as you generate the scale model of the solar system. This is the first time experience for many of you guys. Now you have in your brain something you never had before, right? The scale model of the solar system. And it will emerge to be something you never thought of what it is. Okay. So that shocking experience is what we would like the most here, right? So Saturn is 1.5 kilometers away. Let's get to the next question. How far are Uranus and Neptune? They're farther away, about 4.8 kilometers away. So now you are going to Ratmalana Junction, maybe from the university, right? Too far away from the sun. And the last question: how far is the nearest star from the sun? 40 kilometers. 40 kilometers, even beyond, say, Colombo, right? Peta is like about 30 kilometers, is plus 10 more. Nearest star, we call it the nearest star. Other stars are even farther away. Now you can see all those stars that we see relatively close by are still very, very far from each other. So there's no chance for collision. Okay. The closest star to the sun is 1.5 meters in diameter, 1.5 meters in diameter, and the Proxima Centauri is 40 kilometers away. Now, if you think Proxima is as big as Sun, it's like 1.5 meter to objects 40 kilometers apart. There's no chance of a collision. Okay. Right. So now can we see, okay, out of 1, 2, 3, 4, 5, 6, 7, 8, 8 questions, how many has got, let's say, 3 questions? 3 out of 8. Please raise your hands. 1. That's why I started from 3, because I just counted Delogen. Right. Good job, Delogen. Your guess is right. Have you studied astronomy as a hobby? You can unmute and
Yes, sir.
okay, that's one of the
Yes,
reasons.
sir.
That's what I said earlier, right? Unless you study the science and art, you can miserably fail even with a very, very simple question. If you study, it's something very easy. Okay. Uh, so that's the very nature of different fields. Okay. Right. Right. Then 2 out of 8. 2 out of 8. Right. 1 out of 8. We have 1%. 1 out of 8. Okay. That is, yeah. So have you also studied astronomy, or was it just a guess? That one question you got right. Was it just a guess, or have you studied astronomy?
I already know, sir.
Okay, right. Like that. So, okay, good job, everyone. At least now you know, right, what it is. Now let's move on. So the next thing is origin of the solar system. So I'm going to discuss with you the widely accepted theory of the origin of the solar system, and we call it nebula hypothesis. Still call it hypothesis. Why? There's no proof. It's still a hypothesis. Still a hypothesis. You know what hypothesis is? Somebody says, okay, I propose that this particular thing happened like this. Or somebody come up and say, I believe X is related to Y in this particular manner. Hypothesis without a proof, right? And then what happens in the scientific community is that different people engage in that hypothesis and they test it. They experiment it and they get results, right? And some results are in favor of hypothesis, and the results prove or support the hypothesis, and some results does not support the hypothesis. So that is the fate of the hypothesis, how the hypothesis evolves. If you get more and more data to support the hypothesis gets accepted by the scientific community, and it will be rejected by the scientific community if it gets too many results not supporting the hypothesis, right? So that's how it goes. So what the hypothesis said, and there were a couple of several theories and hypotheses about the origin of the solar system. I'm not going to talk about any of these things except for this particular one, because this is the only hypothesis that survived the test for centuries, and it therefore a lot of evidence to support the hypothesis. So now we believe that this is true. Okay, so it says just few things. What? The gravitational collapse of a small part of a giant molecular cloud. So that's what it says. The first thing, there was a giant molecular cloud. Usually in the universe, if you see up, down, left, right, whatever, you see a lot of gas and dust. A lot of gas and dust. Okay, so giant molecular clouds are there to plenty. Wherever you see giant molecular clouds. Okay, and there was a gravitational collapse of a small part of one of those molecular clouds. So gravity we know, gravitational collapse also we know. It is the self contraction of multiple bodies, maybe gas or dust or small chunks of matter, as a multi-body system. Over the years, they come closer and closer and closer together, okay, because of their own gravity. We call it gravitational collapse. Second bullet, most of the collapsing mass collected in the center, forming the sun. That is number two. When you have a huge cloud of gas and contraction happening, so more and more mass gets into the center. And when you see this lot of mass, lot of gas particles, molecules closer together at the center, they are being pushed by the gravity, on gravity, right? That's the pathway or the process for a sun to be born. For a sun to be born. What is a sun? Sun is a hugely compressed, pressurized ball of gas. It's so pressurized because of its own gravity that at the center of the sun, these hydrogen atoms, they are pushed against each other so hard, so they fuse into helium, giving out gamma rays, energy. And that is that energy that we see coming out of the sun as glowing flare of light. Okay, so that is what the theory says. Sorry, I got briefly disconnected. I'm back. Third bullet, reset rest of the mass flatten around the bulge, right, into a protoplanetary disk. So as you can understand uh, the gravitational collapse is one thing. It happens anyway. Okay, when you have a multi-body system, because of their own gravity, it starts to collapse because gravity does not stop, right? We assume here that there was an initial angular momentum, some rotation around a certain axis. We don't know how we got it because this is what a hypothesis is about. It doesn't have to have proof for everything. You can stand up and say, I think it happened like that, and that's a hypothesis. You don't have to provide proof. So proof or disproof, they all come later. So therefore, this hypothesis presume that there was angular momentum initially. So now we can think about a situation where this gas cloud rotates around a certain axis, and because of its own gravity, it collapses also. So two processes are happening at the same time. So because of this rotation, the three-dimensional structure eventually turned out to be a flat disk kind of structure. The disk has a plane. Earlier it was a three-dimensional structure, but now it's more like a plane. And within the plane, you have the whole matter of the initial cloud now is like flat disk. And within the disk, right, the planets were formed, planets, moons, asteroids, and other small solar system bodies. They all were formed in that disk. Now, this is what the nebula hypothesis says, right? Very simple, 3 lines. Now, I can show you some of the pictures here. See, you have seen these pictures from Hubble Space Telescope and other ground-based big telescopes. What do you see here? This is part of the sky randomly. You can see a lot of colors here because of the gas. This is the emission of various different wavelengths based on their chemicals that they have, right? Gas cloud, very much like this molecular giant gas cloud that the hypothesis mentioned. Okay. In the nebula hypothesis, the cloud, giant molecular cloud, could be much bigger than what you see over here. But you can see the gas cloud. So it's not a strange thing. The hypothesis says about something that you can even see now, right? They're there. And also you can see small chunks of matter. You can see an asteroid here. So that's about the third one. Rest of the mass flattened around into a planetary disk. Okay. So on the disk or in the disk, the matter got together, collapsed and collided and attached together, right? One particle by one particle, one by one particle, and gradually they develop into a body, small body like this. So therefore, we have seen evidence, right, to prove the hypothesis. Right. So I think it's we have few minutes. Let's continue till 7. So who actually brought forward the nebula hypothesis? Actually, it was put forward in 18th century, 1755 to be exact, by German philosopher Immanuel Kant. I think you have heard of his name, Immanuel Kant. And then modified in 1796 by this person you know, everyone knows, French mathematician Pierre-Simon Laplace, the same Laplace who invented Laplace transforms, okay? So, so therefore, this is, I think, related to you, right? So after the initial proposal and the development by Kant and Laplace, it was not given any serious thought back in the day, because the only way for somebody to give it a thought is by way of submitting results, evidence. And to get the evidence for this kind of theory, you need to have equipment, telescopes, imaging instruments. We didn't have that back in the day. So therefore, it took a while, right, to generate some sort of evidence for this one. There were some serious considerations came along the space age in 1950s, only 1950s, okay? And in 1980s, very recently, relatively, right? Acceptance with the observation of young stars being surrounded by cool disks of dust and gas. This is exactly what the hypothesis said. Now, we have photographs of what? Young stars, not the old stars, young stars, okay? Surrounded by cool disks of dust and gas. My God, this is exactly what the nebula hypothesis says. There was a big molecular gas cloud and started rotating around an axis, and because of self-gravity, it collapsed and became like a flat disk. And in the disk, planets were formed. Now we have evidence. So with that kind of evidence, it is very hard to disprove the theory, okay? So in 90s, the theory was strengthened by the discovery of extrasolar planets. My God, this is another big support for the theory hypothesis, extrasolar planets. Now, that's another discussion for another day, extrasolar planets. Have you seen planets out of the solar system? Right? Yes, there are, but we have not photographed them. We have seen them using different techniques. Okay, there are extrasolar planets. So there's a sun. There are planets going around the star. Right. Sometimes the planets are big, relatively big, so that you can see some gravitational perturbations of the sun. Right. So we can discuss that later. But we have seen scientific evidence of other extrasolar planets. So the evidences were mounting one on top of the other, right, to prove the case. So that's why nebula hypothesis is so widely accepted by the scientific community, right? So any questions? Quick questions before we wind up for today. Right. So I will upload the video and the slides to the Moodle so that you can refer to that later. So with that, we will wind up for today. I'll see you next week. Have a good evening.